Kicking off our next session is none other than, I don't know if Colin, you want to introduce Ganesh. I mean, I will say that I'm an IITB alumnus, so I'm very, very proud to have Ganesh here, but Colin, go for it.
Hi. Yes, I'm very excited to introduce our next speaker, Ganesh Ramakrishnan. He's currently an Institute Chair Professor at the Department of Computer Science and Engineering at IIT Bombay. His areas of research include human-assisted AI, AI in resource-constrained environments, learning with symbolic encoding and domain knowledge in machine learning, and other areas of efficiency in machine learning. He's Ganesh has received awards for his research, such as the IBM Faculty Awards and other awards from Qualcomm, Microsoft, as well as the IIT Bombay Impactful Research Award. And at Abacus, we've been very lucky to collaborate with Ganesh recently. And so I'm very excited to hear this talk. So Ganesh, please take it away.
Thanks, Colin, for a very generous introduction. Thanks for hosting this talk. I'm just going to screen share. Can you please confirm that you're able to see my screen?
Yes, we can see your screen.
Thanks. So I'll give a brief overview of a platform that myself and my colleague Rishabh Iyer at the University of Texas at Dallas have been building with a whole bunch of our students, both at IIT Bombay and at UT Dallas. The idea behind this platform is to make it possible for people in resource constrained environments to be able to build models both in data efficient and compute efficient manner. So the talk is meant to present our open source toolkits, and you'd really like to encourage the audience here, the community at large, build upon our toolkits in two ways. Either you can integrate new algorithms, or we'll be very happy if you could use these toolkits in your applications. We're all aware that deep learning has achieved near human performance in multiple fields. There's a strong growth in both in the complexity of the networks as well as the number of networks. The issue then is, has deep learning been solved? Yes, deep learning has reached human performance in several tasks, but the problem is that you need large data sets and massive models. In addition, there could be issues of fragility owing to biases in the data. There could be massive label skew. In addition, the process of labeling data itself is very expensive. Just to give you an insight into the kind of cost incurred in the compute-intensive deep learning models, for example, to train a BERT model in Wikipedia and book corpora data set, you could incur 200,000 USD, whereas for a single deep model for NLP with network architecture search, you'd incur 237 million. I mean, this is INR Indian rupees, but $3.2 million. So you can also measure the impact in terms of carbon footprints. The other aspect is labeling cost. The labeling cost, of course, increases as you go from image to text, where the cognitive load is high. And we also presented representative numbers for other labeling tasks. So overall, there is need for data preparation, model training, model validation, and model deployment. And at each stage, there is cost. Could we be both data and compute efficient across this pipeline? The constraints are that you like to reduce your labeling or be efficient and effective in your labeling, and also be robust in the process to distribution shift. A common framework that we would exploit through all our modules is subset selection. You have a ground set V. This is the ground set V of all the data points. And what we seek is a subset of points that's as good as the ground set with respect to an information function f. Now, what kind of subset selection are we after? So we could look at selecting subset of a labeled data set so that we could reduce the training time. And this is typically what happens when we have a cold start setting where we don't have, I'm sorry, when you have a warm start setting, when you have lots of labeled data. But you also have the cold start setting where plenty of unlabeled data, very little labeled data. And in such setting, you would like to reduce the labeling cost. There are other settings like, you would like to select subset of model parameters to reduce inference time and so on and so forth. There's been a lot of research in this direction over the years, of course. And here's a bunch of keywords, a representative of the approaches used in this area: greedy, representation learning, meta learning, semi-supervised learning, streaming, submodular, and so on. But the issue is that there's been a lack of good toolkits and benchmarks in this space. So what we're going to present is Distill, data efficient machine learning, which has several modules. I'll begin with Submodlib, which is at the heart of all the other modules. Submodlib is a library for summarizing massive data sets using submodular optimization. What is submodular? What's a submodular function? Here's a simple representative example. Consider f, the function, which is a number of distinct colors of balls in an urn. On the left-hand side, you have the set A, and on the right-hand side, you have set B, a superset of A. You have a ball, which is V, the blue-colored ball. The marginal gains of adding the blue-colored ball to the smaller set A is greater than equal to the marginal gain of adding the same ball to the larger set. Such a function is a submodular set, a submodular function, and submodular functions exhibit this diminishing returns property. What we have in Submodlib is extensive documentation and several submodular functions and their maximizations all implemented. Installation is as simple as a pip install described here. What are the different classes of submodular functions? Broadly, 3: representation, diversity, and coverage. But you could compose these with queries that seek information or queries that try to hide information. So in this first case, you see the query person seeking information on person as a representative, diverse, or high coverage summary. And therefore, you'd like to ensure that the selected subset has people, but then they must have people in different poses or different people. On the other hand, the second case, you'd like to hide the person information. We'll see how both query and privacy could be slapped on each of these classes of submodular functions. So let's look at the broad outline of instantiations of said functions. Representation functions include facility location, graph cut. Diversity includes dispersion functions, determinantal point processes. Coverage functions include set cover, probabilistic set cover, and feature based. Importance functions are largely modular functions. They're basically submodular, and the negative is also submodular. The information functions, which I alluded to in the previous slide through the example of queries and privacy preserving set, these are encapsulated in mutual information and conditional gain, and these could be used in conjunction with all the others. There are a bunch of others which we won't talk about today: discounted cost functions and complexity functions. Some of these become more interesting when you're looking at submodular minimization. So We'll next look at information functions, which we would invoke once we outline examples of each of these three classes. Information functions have traditionally been very popular through entropy. We are aware of discrete entropy, the joint entropy of variables indexed by S in this case. And this discrete entropy turns out to be a submodular function. But what you see here is the conditional gain, the gain on adding E to A. Because discrete entropy is submodular, obviously there's diminishing returns. Now, this conditional gain itself has some interesting properties. That's what is highlighted here in yellow. But you could also have mutual information. Now, it turns out that mutual information and conditional gain could be composed with any other submodular function in place of entropy. So this is a more generic definition of submodular mutual information. If A, comma Q is the function applied to A plus the function applied to Q minus the function applied to A union Q. And basically it's measuring how relevant is this set A to the query Q. On the other hand, the example of conditional gain, now generalized to submodular function classes, is measuring the irrelevance of the privacy set P, irrelevance of the set A to the privacy set P. And what you see below are instances of both mutual information and conditional gain applied to the different classes of submodular functions. So Submodlib presents a unified framework of extractive, query, and privacy preserving subset selection, where you could look at extractive. You're trying to maximize the submodular function, identify a subset constraint. In the query sensitive subset selection, you're trying to maximize a mutual information function for any reasonable choice of F, the submodular functions, the recipe that we have provided. And you could do the same with conditional gain. Finally, you could also put together the query relevance and irrelevance to the privacy set through the conditional gain mutual information CGMI functions here. Of course, we have some degenerate cases which correspond to when the query is the entire ground set, or when the privacy is the empty set. So let's look at representation functions. A canonical example is of facility location. You want to identify some K facilities such that these facilities cater to the market at different locations, also possibly raw material supplies. So the points here in red are the facilities, but there's a cardinality constraint you typically have. You would want to locate K facilities. Now, underlying the choice of these facilities is the similarity between any two pair of points I and K. And the facility location problem is to identify for every point I in the ground set the most similar facility K. And overall, you like to say maximize the facility location function, identify a subset X that maximizes the facility location function. You could likewise have a saturated coverage where you're looking at coverage, which we'll talk about a little later, but then you are also clipping the value based on an alpha I. Or graph cut, we're looking at a combination of similarity between the subset and the ground set while discounting for self similarity within the selected subset. And what would representation functions do? They would try and pick representative samples from each of these clusters while possibly leaving out outliers because they're not really worth representing. So effectively, these would pick centroids. Now, what happens if you apply information functions to facility location? So you see here the FA is the max. And when you now look, when you put in the conditional gain on B, you're basically now discounting for the max similarity of every element in B from the max similarity of every element in A. Okay. So on the other hand, if you look at mutual information between A and B, you're looking at the min of those max similarities. The next class is coverage functions, where you're trying to cover a bunch of concepts, maybe keywords here: cat, dog, bird, man, beach, and you'd like to identify a subset of documents that cover these concepts. Or you might be trying to cover objects, male, car, greenery, etc., and in that process identify a relevant subset of images. So the basic idea is to select instances which cover all the concepts. You could also have a probabilistic version where you have the probability Pij of an image I covering concept J, or a document I covering word J. Yeah, this allows for probability of covering concepts. And you could again have mutual information variants, um, as well as conditional gain variants for weighted set cover, and probabilistic set cover. Finally, you could also have feature-based functions where you're looking at coverage through the feature space. And typically you would use a concave or modular function. So the total contribution of each feature U in the set of images S could be a modular function, and concave or modular gives you submodular functions. And you could also have now a composition of these through deep submodular functions. Final class is the diversity class. We are all aware of how you would capture the volume of the points through the determinant, right? The volume of the polyhedron that encapsulates points through a determinant. Now, in the case of DPP, you're looking at similarity between pairs of points. The log det LS, the submatrix spanning the subset of points through the similarity kernel. This turns out to be a submodular function. There are, of course, other diversity functions as well. You would not expect all diversity functions to be monotone in general, because as you keep adding points, you would not necessarily expect the function to itself increase. But yeah, several of them are submodular or exhibit submodularity like properties. So the idea here is picking items as different as possible, and you notice that in this process the outlier has been picked, which was left out when we consider the facility location or the representation class of functions. You could likewise also do dispersion min, dispersion sum, dispersion min sum. Sum and dispersion min sum min are not submodular. Dispersion min sum is. So as a summary, we have a bunch of submodular functions. Several of them are monotone. As I mentioned, the log det is not a monotone submodular function. Likewise, graph cut and mutual information aren't. But there are also non-submodular functions such as disparity min and disparity sum. Now, you could slap the mutual information, conditional gain, and combination of these on all of these functions. This is a table not necessarily meant to be parsed in such a short duration, but sufficient to highlight that all of these have been implemented in Submodlib, rather the maximization of these functions. So what are we talking about in terms of maximization? We'll get to that now. The master optimization problem is that you want to maximize this function f, which could be either the submodular function, mi function, cg, or cg-mi function, subject to some cardinality constraint. Let's get some glimpses into variants of this master optimization problem. The most intuitive algorithm is a greedy algorithm, And the idea here is just pick the next element E, which leads to the maximum gain. Um, how good is a set Sk composed of the first k greedily selected elements? It turns out that it's not that bad at all. Um, this constraint, of course, is the cardinality constraint. Um, and it turns out that Sk has an approximation. This entire algorithm has an approximation guarantee. In practice, of course, it's very good. So you can see that for a problem of that of sensor placement, you're trying to place sensors to cover field. Um, the greedy choice is almost as good as optimal. In theory, it turns out that the function evaluated on the greedily selected set is at least 1 minus 1 over 1 over e times the function evaluated on the optimal set S star. And this is quite encouraging, though, of course, as I said, in practice, uh, the results, the greedy algorithm often does as well as the brute force. However, it turns out that no polynomial time algorithm can do better than this in the worst case. So this is pretty reassuring. Um, you could also have budget constraints. Instead of giving the equal weightage to every element, you could have a CE, and in which case you do a greedy as well as a modified greedy, where you are accounting for the cost of the element while looking at the conditional gain. And it turns out that it has half the previous approximation factor. Um, but there have been, of course, several other investigations into this space. Um, Summarily, the greedy algorithm framework could look at uh, cardinality, or a weighted cardinality, or a weighted cost constraint, and you could look at maximizing either monotone submodular functions, in which case you have the encouraging guarantees we talked about, or in many cases submodular functions without monotonicity. And this is the overall greedy algorithm. It turns out that Submodlib makes this entire space, which could be somewhat intimidating to a newcomer. Um, it makes Submodlib basically makes it very easy. Just a few lines of code. Here you see you could use specialty location to identify this diverse set of points in purple here. You could use FLMI, where you have this query here in green, and that has influenced the choice of the subset of the same cardinality. And you can see that the green has drawn a couple of points close, a couple of the selected points close to the cluster where it belongs. On the other hand, you could also have a conditional gain. All you need to do is just specify this red point as the conditioning query, conditioning privacy set, and suddenly you find that the points are selected points are all pushed away. So very easy to visualize as well. Now we look at a couple of other modules in Distill where we have leveraged Submodlib or built significantly on top in a very non-trivial manner. The simplest extension is Trust, targeted subset selection to mine rare events, personalization, fairness. And I've also kind of divided the remaining part into the cold start, that is Trust and Spear, and subsequently the warm start setting. The cold start setting, we basically are struggling with label data. So we don't have too much label data. So what can you do in the case of less label data? So imagine that you have a large unlabeled pool, and you know your target domain. For example, you might be looking at anomalous behavior. Your target is all nighttime images, whereas your unlabeled data set has day and night both. So the uh, use of mutual information based functions could help you identify a targeted subset that is aligned close with the target that should be labeled in order to do well on the target domain. Um, and this is enabled through Trust, again extensively documented and very easy to play around with. There are many use cases. For example, if you may have, um, you may want to tune your model based on the behavior of the confusion matrix, where you would like to identify target classes through the diagonal elements, or you'd like to condition or guard yourselves against the confusing classes based on the off diagonal elements. So you can do performance based data selection. As I already mentioned, you could do rare class enhancement, selecting and labeling rare events to improve the model performance, like in the case of the nighttime images. Or you might do targeted selection for personalization, such as handwriting personalization. Yeah, more about that in our recent paper at AAI 2022. But all this is available in Trust. And yes, Trust not only has the submodular functions and the MI functions, but also combinations of MI and CG functions. Um, and yes, there are some representative results on how Trust helps improve performance on rare class and performance based selection. In the interest of time, I think we're already running very late. Um, so I'll refer you to our paper where we have more detailed experiments and a couple of actually follow-up works which are also on archive, where we talk about the use of such a setting in semi-supervised settings for medical data sets as well, where the problem is really of finding a needle in a haystack. And you'll find that each of these functions contributes in a very different way. For example, log.mi, which is meant to get you diversity. You can see very impressive performance in terms of gain and accuracy with respect to the budget. um, Spear is another slightly different dimension to the cold start setting, where you don't necessarily identify the labeled set through the initial exemplar set, but you may also have rules or programs. So Spear leverages data programming through and subset selection. Um, I'll illustrate now through a natural language example. So imagine you were trying to classify questions such as in the TREC data set. If the text contains how, you would think of the question as being a description question. On the other hand, if it contains how long, you would think it's a numeric question. Now, obviously, you can see this conflict between these labeling functions, and therefore it becomes important to aggregate across these. So the LA is a label aggregator. Of course, these are simple examples. You can have more complex examples where, given pairs of entities, Barak, Michelle, etc., you like to identify whether they are spouse or not. And in text, it's often not very difficult to write simple rules labeling functions, which may not be uh, extremely robust, but it might form excellent starting points. And the idea is, once you design these weak labeling functions, you can apply them on data through label aggregators and therefore generate your label set. And that's been a typical paradigm. A Spear allows for that. Again, it's very well documented and very easy to use. You could also do this through images. In the case of images, you could, in the case of Google Album, you are organizing the photos into folders, and you can add photos to an album X when the photo contains a particular person name, and then you could therefore identify other images which look similar to that initial image, which could act as an exemplar. Now, this way you could create albums and rules through exemplars to automatically add photos to the album. However, there could be issues. For example, you get incorrect classification. This image is of the wrong person being tagged as maybe a Sundar. It turns out to be one folder. So what we allow in Spear is multiple aggregators that would allow you to weed off the wrong signal you're getting through spurious incorrect classification through exemplars. We've implemented some of the aggregators from Snorkel from Stanford, but we have our own aggregators, beginning with Cage from AAI 20, where we bring in priors associated with the labeling functions. So when the person writes a labeling function, often the designer of the labeling functions is able to associate some confidence, at the least saying that the labeling function 1 um, is more plausible than labeling function 2, and which is more plausible than labeling function 3. So simple insights of this form could lead to significant stability in an extremely unlabeled setting that we are dealing with, unsupervised setting that we are dealing with. However, in more recent work, we have graduated beyond that. So unlike the conventional data programming approach, which lets you generate the label data and learn discriminative models subsequently, more recently we've been working on joint approaches, which are also reflected in Spear. The idea behind joint approach is that not only are you given the labeling functions, but you also may have small amount of label data which could be identified through something like targeted subset selection. And eventually what you have is a jointly trained model, a model that doesn't just take the output of the generative model and threshold on the probabilities to get a discriminative model, but which jointly learns on the label data set as well as the labeling function model. So here are some of the state-of-the-art algorithms that are implemented in Spear. Some of these are ours, but um, several of these which I am marking, their other state-of-the-art approaches which are implemented. And the basic idea is semi-supervised data programming, where you have a feature model, could be any deep feature. For a feature, it could be the BERT based representation, which operates in conjunction with the labeling function model, which is marked in blue out here. And the idea is you would like the feature-based model to agree with the ground truth labels on the label data, have low entropy on the unlabeled data, a thresholded version of the labeling function model should agree on the feature model on the unlabeled data. And you may not want to threshold, but rather make the probabilities of the labeling function model and the feature model agree on both the unlabeled and labeled data. Now, it's not necessary to have all these components, and we report very interesting combinations that work with intuitions. The last component is this precision guide. I gave this example of how you could maybe prioritize labeling functions over each other. The person designing the labeling functions very well knows intuitively how good the one labeling function is in comparison to another labeling function. So these precision guides play a very significant role in bringing stability, and these can be also tuned or set on validation data. So uh, the other component here is that the label data itself, which appears in a couple of places here, does this label data have to be identified in an ad hoc manner? Well, no. This label data could be also intelligently selected. And here's an example. The machine could come back to the human and say, well, you seem to be, your model seems to be confusing between these two people. Are they the same or different? Right? So this kind of proactive data subset selection could be with the goal that the selected subset should complement and not necessarily subsume the labeling functions. And that's exactly where our work on conditional gain or privacy preserving variants come handy. To give another very simple example, you see these labeling functions LF1 and LF2, which seem to be fairly confident on examples S1 and S2. LF1 says that S1 is a spam, LF2 says that S2 is not a spam, and they also tend to agree with each other. However, on S3 and S4, the labeling functions seem to be totally confused and they are actually contradicting each other as well. So this is the subset that would be worth labeling, because this subset gives you insights beyond the labeling functions. And that's exactly what we've been also looking at, how we could combine different subset selection schemes in conjunction with the labeling functions. And here's one simple example that our approach performs significantly better than even handpick. So if we were to handpick the labeled examples, you would not necessarily be making the wisest choice. Instead, if you let the model pick the labeling, the labeled examples to be labeled, you would benefit the labeling function model as well. um, I would now very quickly present an overview of the other two settings. One is, and both of them operate in the warm start setting when you have sufficient amount of label data. But I must tell you that this notion of warm start is also a bit relative. I mean, as you keep growing your data, you would also need to make sure that you don't have model drift. So we talk about that in Distill subsequently. Deep interactive subsets and data subset selection. The goal is to maximize the deep models. Um, I mean, all of us familiar with support vector machines would know how the support vectors can make a world of difference in inbox settings can be obtained through core sets or sorry, did you lose me?
We can hear you now just fine.
Oh, it was just momentary, I hope. Yeah.
Yes.
Okay, thanks. Um, so in Chords, we present a whole bunch of core set and efficient training mechanisms. Um, these are some use cases of Chords. You could do efficient, robust, supervised or semi-supervised learning. You could also do efficient hyperparameter tuning by using small subsets of the label data. And we're very happy that there's some investigation on network architecture search that we're doing with Colin and the Abacus team. So there are several algorithms implemented within Chords. The list keeps growing. Some of them are our own works. I'll talk about a couple of them. I'll specifically talk about Glister and Grad Match because they do, in some sense, also subsume some of the others. So let's begin with Glister. What's the idea of data subset selection in Glister? You're given a training data set U on which you can measure your log likelihood. Typically, you would estimate the parameters thetas on the likelihood function evaluated on the training data. However, we are also assuming that we have access to a validation data, and this is typically used for parameter tuning, but we would like to make um, use of this validation data in a slightly different manner and more tightly integrated with the training process itself. And that's what we try to do in a couple of our works. Um, so one important point here is, as we seek a subset of the training data such that the resulting model performs the best with respect to validation, we would like to make sure that the subset selection algorithm is as fast as possible. Obviously, you don't want the subset selection time to eclipse the overall training time. And also in the process, can we show theoretical guarantees for such subset selection schemes? So how do we select the right data for efficient and robust learning? So our approach is select a subset that maximizes the validation log likelihood of the model trained on the training data subset. So subset is on the training data, whereas what you're measuring is the validation log likelihood. The parameters are estimated on the training data subset. And let's see how that happens. So here in the inner optimization problem or inner aspect, we're looking at theta is estimated on the subset of the training data. But on what grounds are we identifying the subset? Well, the subset should be such that the validation log likelihood is maximized. That's the outer level problem. So, well, is this even feasible? Well, instead of validation, we can also use a full training data set. That's just a side note. Um, the challenge is that the inner optimization problem can be very difficult. I mean, you need to solve this every time you identify a subset and then go back and identify the next subset. Right? So that could be an issue. Solving the inner optimization problem can be very expensive. Um, and if you go to do it in closed form exactly, obviously, or even attempt to do it in to convergence, it can defeat the purpose of selecting a subset for faster training. Now there are some reasonable forms you can derive when you're looking at naive Bayes or nearest neighbor. We don't talk about that, but that's dealt in prior works that Rishabh Iyer has published. But what we're going to do is look at approximations for speed up that could hold for more complex and real worldish law, network models and objective functions. And what is that approximation? Well, the first is online one-step meta approximation. So you take the one-step gradient update, single gradient step towards the training subset log likelihood ascent direction. That's the first. And now based on this, you could identify the subset every time again, but then that also is expensive. So just because you have plugged this theta here doesn't mean that the subset selection now is going to be fast. So of course, before we move to other practical aspects, let's look at some interesting properties. So when the validation log likelihood function is the negative logistic laws or the negative squared laws or the negative hinge laws, the above optimization problems is an instance of cardinality constraints or modular maximization. In the special case of negative cross entropy laws, we have weak submodularity, which we won't talk about here. Um, we recall that submodularity has this natural diminishing returns property, and therefore we can use this, and you can also use a simple greedy algorithm to find the data subset is. Right? But as I pointed out, this is also going to be expensive because you, as I'm going to talk about next, the evaluation of this function for every element that you try and add is going to be very expensive, a greedy algorithm, right? So instead of working with this complex objective, how about a Taylor series expansion so that you can further approximate the optimization problem ignoring higher order terms? And what you observe is now the influence of the subset is only in the second term. The first term is just the previous iteration of theta used to evaluate the log likelihood and the entire validation set. So this is done at each iteration of the greedy algorithm. And as you can see, this dot product in fact opens up many other avenues. One of them is of course that this greedy subset selection scheme now only needs to identify this dot product for every new element added. So it reduces basically the need for multiple forward passes over the validation data. That's exactly what we have now gotten out here. So this is different from, of course, doing Taylor approximation upfront. We did this Taylor approximation after the one-step gradient approximation. Otherwise, you would have just had a modular problem. So now, so what do you get because of this? Well, we can now do stochastic gradient descent on an initial set, get the parameters, and on the new parameters, you can again do a greedy data subset selection based on which the new set of parameters obtained. So alternate between the parameter updates for L for a couple of epochs and the subset selection. So data selection is done every L epochs. There are further computational aspects. In the interest of time, I just want to mention them. So we could select a subset every L epochs. We also think of use engineering tricks such as large layer gradients only being used, and also stochastic greedy selection and R greedy selection algorithms are used for subset selection, which do pretty well in practice. So I didn't get the time to talk about multiple greedy variants implemented within Submodlib, but some of them are as good as the greedy in theory, and some of them in practice turn out to be as good. So what's interesting is that under certain condition, Glister Online, Convergence Optimizer, of the validation loss in 1 by epsilon square kind of epochs. And the upper bound that we get for the difference in the validation loss with respect to the optimal parameters has this interesting cos theta, which measures the dot product between the training likelihood gradient and the validation likelihood gradient.
Sorry, Ganesh, just to
Yeah.
step in, deep apologies, but some of our panelists from our next panel have to leave soon. Is
Okay.
there any way to wrap this up in a minute?
Yes, I'll
Yeah,
be doing it soon. Yes, I'm
thank you.
almost done. Yes, thanks. Yes, so very few efficiency results. You can the main takeaway is that we get almost 3x speed up with no loss in accuracy, and if you're okay with little loss, you can do better. And 10x speed up for auto ML, which is with hyperparameter tuning and no loss in accuracy. And there are also robustness results where we again see consistent speed up. Um, the last component of our work, the Distill work, which I'm going to just talk about how it builds on chords, but there are many other things we do in Distill. The idea is to cut down the labeling cost in a warm start setting. Again, Distill is very easy to use. What's interesting about Distill is that we allow whole bunch of active learning algorithms, state of the art, to be used. Where the human can use that algorithm to identify the subset to be labeled next. Um, and it also makes it very easy to switch the active learning algorithms with different implementations of common deep neural networks. And another very important thing is we allow for data augmentation, which often eclipses any gymnastics you might do with your active learning scheme. So data augmentation is very critical here, and that basically makes you work hard on the active learning strategy to show its value. Um, and a couple of other engineering aspects here as well. And these are the algorithms implemented. But specifically with the Glister, which I talked about earlier, we do Glister active, where you select a subset of points epochs to be labeled and add it to current label set. So you basically now you can use hypothesized labels in Glister active instead of working with the true labels. That's because now we also want to deal with unlabeled data points. And yeah, this Glister active has been profiled here, but yes, you're welcome to visit our paper. And also the takeaway message is Glister can achieve 7x speed up at 10%, 3x speed up at 30%, and you can see as you increase your you're okay with compromising on the loss, you get more speed up. And that's all with active learning as well. Right, I'm going to skip all this in the interest of time, and a whole bunch of leaderboards have been set up. And the most important thing is we've been able to make extensive use of our work in several applications at both at IIT Bombay and elsewhere. We've had award-winning works on video analytics for the Indian security agencies, where we have made extensive use of efficient, effective data subset selection. I've been also working with Abacus, IBM Research on efficient AutoML. We made good use of this for low resource language settings for optical character recognition and machine translation, especially post editing for low resource languages. We made extensive use of Spear and Trust there. And likewise for personalized speech recognition, we made use of Trust. And we have upcoming very interesting use cases of all of these in biomedical imaging. Thank you. Thanks for your attention. I hope you'll all take interest in making use of the libraries I talked about under data efficient machine learning. Thank you very much.